So welcome to demonstration video 1 on ST1 describing data. So today we're going to briefly go over some theoretical details that we talked about before, before going through some calculations in relation to discrete variables and then also sampling. So what we're going to talk about briefly then is calculations in relation to these two topics, and then we're going to skim over what you know already in terms of the theory, and then Lab 2 is going to cover the data summary and data visualization parts. So we know that our aims in this course are to look at statistical terminology and the concepts and use that to inform better design for experiments and sampling approaches. And that means we'll understand our data better, and also be able to plan ahead for experiments and understand better how many samples we may really need and what questions they can actually answer. This will mean we can better consider the sources of error in our design and also consider what types of data we have in terms of also presenting them to a reader. So we talked in the introductory videos about how we need to understand our data in terms of understanding what test we have and also what test is appropriate for our data given the considerations that may be associated with it. This is not an easy path to go through, nor is it simply like a straightforward path like this. It really depends on what things we find out about our data. So exploring our data is very much kind of a journey to see what's there. In the example, we had this kind of question for you to look at what kind of data types each of these are, and we'll talk about that during the lab itself. We also talked about discrete variables such as rolling dice and how you can use a binomial probability as given by this formula here to calculate that, where you have n choose k, where you're looking at observing k events out of n possible, and p is the fraction of the probability of that event occurring, and 1 minus p is that probability of that event not occurring. So for dice, p is 0.5 and 1 minus p is also 0.5. But also, just like binomial models, we have multinomial models. If we have, say, a dice where we have 6 different outcomes, instead of just coin tossing, we can compute those probabilities in a slightly more complex formula. We went through in the formula how we can apply that. We can also apply that using for more complex numbers using R code. So instead of trying to do these calculations by hand or with the calculator, we can use the choose function in R to do this for us. And then 2 asterisks means that we're 0.2 to the power of 80 and 0.8 to the power of 220, depending on what way you want to write it out of those options. So then we can address these questions. So say you have a cow inoculated with FMDV and they have a 30% chance of becoming infected. We can use that formula then to think if we have 6 cattle, what's the chance that 4 out of 6 will be infected? So we can think of our 6 choose 4, and we're going to multiply that by 0.3 to the power of 4 in this case, because that's probability of being infected, and then 0.7 to the power of n minus k, which is 2 in this instance. And we're able to work that out and to determine that probability. In the same way, we can ask, what's the chance that none will be infected? So in this case, you have 6 choose 0, and then we have 0.3 to the power of 0 and 0.7 to the power of 6. 5 out of 15 is the same thing. 5 choose 15 by 0.3 to the power of 5 and 0.7 to the power of 15. So that brings us to the more complex area of sampling and experimental design. So we talked about how we can apply simple random sampling with R using code like runIf that will generate 3 random numbers in this range of 0 to 30. And we can toggle those features depending on what we want. We also outlined how we have a balance between accuracy in terms of inferring features about the overall population based on our sample versus precision, where we want to look at individual effects within that sample only. So we have a true random sample which is unbiased and also accurate, but this may lack resolution about the subgroups within there that might be of interest. And And ways to tackling that would be to increase the sample size, but that's not always straightforward to do. We looked at how crossover experiments is a good example of how we can do that. And other approaches are randomized block design, where we allocate samples to different components of variables as well. We looked at how with crossover experiments, we could have a time axis going across here. We have 3 different time periods, and then we have 6 groups or 6 hosts, each of which has a different pattern here in terms of the sequence of the 3 treatments that they undertake over the time periods. So each unit, each host will get a different treatment at each different times, and then they cross over into a different treatment. So we go from A to B to C here. We also looked at Lab1 square allows for more balancing. So we want to make a balanced design such that A can carry over to B. We also have A carrying over into C, A carrying over into D, and A carrying over into A as well, so that A is strongly balanced, as well as having the same situation for each of these. Obviously, we have 4 groups here, which works well. But if we've more an odd number of groups or something that doesn't quite conform, we have to make sure that the carryovers are relatively balanced where possible. We looked at how we can then infer models from each of these. So for our first cell there, so say this cell down here is A1, we could then infer that there's some sort of baseline effect. There's some treatment effect from the sequence A. There's some sort of time effect from time period 1. And then there could be some kind of sort of carryover, but the carryover here is going to be 0. And that reflects variables in this cell. Whereas if we take A from a different cell, we're going to get the same baseline measurement for A plus the treatment effect of A. But we're looking at time period 3, and the carryover is from D in this instance. So that means we will find that the carryover effects will have an effect on our observed value. So this is all to observe our some sort of observed value for that particular cell. So we can create models like this we outlined before. So here we have mu A plus S for A and T for time period 1. For this box here, where this is A1, this is B2, this is B2, sorry, that's B1 over here, and we have A2 down here as well. And as you can see there, we have a slight issue because if we average the effect of A1 and A2 here, that means we're going to get, so looking at the average effect of A across those 2 sets, it's going to be the average of these 2. So mu A plus S plus T plus mu A again minus S, because the different we should see symmetry between the treatments, minus T for the time effect. We're just looking at a simple binary difference, plus the carryover effect from that group B. So this can be summed over 2, which would give us mu A plus the carryover effect of B. So that means if CB is small, then it should be okay. But if not, then we may have to work further on this. So we also looked at equivalence and non-inferiority. So for the typical study, we're used to comparing one group, maybe a placebo group, compared to a treatment group, and trying to identify if there's a difference between those different groups based on the features that we have available. But if we look at equivalence, we're saying that the 2 different treatments don't show any difference between them, such that their confidence intervals or credibility intervals, or whatever type of intervals you're using, lie within each other. So you see, this is the old treatment. This was its, you can see it's one times its variance coming out here. You can see that the new treatment which has a mean slightly lower, its confidence interval falls within this range. So that's equivalence, whereas non-inferiority means that the lower bound of that new test is not below that of the existing test. It may be better on average or maybe slightly worse, but the key point is that the interval does not exceed this one here. We also looked at previously, what is the question? And we looked at this idea that most of the time we're doing inference, assuming that we have multiple data sets to explore and that we have described them properly already, that we can follow this path to go through our studies. And it's seldom that we're actually making predictions for our individuals. And it's unlikely that we're looking at average effects or just determining different effects if we're looking at comparing different measurements affecting each other directly. So we can then think about questions that are related to this area. And question 5 was for study A and B here. So looking at a whole bunch of infected and uninfected chicken thymus issues. If you sample A, study A, and you're looking at protein A, you look at 20 samples allocated using random numbers generated with R. That means that's a simple random sampling. B looks at protein A again. It's using 10 infected and 10 uninfected samples. Because we're creating a stratified approach here, looking at 2 different strata within the freezer, that means this is stratified random sampling. So here, A tells us more about the underlying features of protein A across the whole collection, whereas B tells us more about the underlying features of the protein A level in the infected and uninfected cells. So B tells us more about it's biased, and it tells us more about the difference between the infected and uninfected, whereas A tells us about the overall patterns across uninfected and infected together. So technically, study A is more accurate in the literal sense of accuracy, but they're focused on different things in essence. We can look at question 6 as well. So looking at numbers of bacteria per petri dish in a large collection of big species, what type of sampling is done in each case? So if we take a sample of 100 petri dishes by selecting 10 for each of the 10 species, that's a kind of a stratified form of sampling because we're sampling each of the 10 species. So again, it's like our example for the infected and uninfected cells. If we use random number generator to select a petri dish from the numerical IDs of all the petri dishes, starting with that petri dish, every 40th plate is chosen until 100 plates are in the sample. So that's systematic sampling because we're taking every 40th. A completely random method is used to select 100 petri dishes. Each petri dish has the same chance, number 3. That's simple random sampling. The species is numbered 1 to 10. Random number generator is used to pick 2 of these species. All the plates in these 2 species are in the sample. So that's cluster sampling. And then if you're asked to grab the first 100 plates you can find in the freezer because they need them ASAP, that's convenience sampling because you're just taking the ones that are at hand. So let's also think about this question where you have 3 monoclonal antibody treatments and 9 cows to be inoculated with them. So you can think about lots of variables here. So this is maybe a question that you can that has no end to it really. But you can think about how you might set up this kind of treatment if you have 9 cows. So you might have in essence to think about the 3 different treatments they've tried out A, B, C, and if that's a pattern for 1 cow in 3 time periods, 1, 2, 3. Then we have time as 1 variable. So this is cow 1 here. We could cow 2, 3, 4, 5, 6, 7, 8, 9. So then we want to change it for 2. So let's say we do B and then A and C. So here we've thought about the one before. So A in capital 1, we've A carry over into B, B carry over into C. So here now we have B going into A and A going into C. So you have two different carryovers in the revised version. In the same way, we could have C. C has not carried over either. So we've got C, A, B, and the other one will be then C, B, A. In the same way, we're also going to want the symmetric ones of A, B, C. So you got A, C, B, and BCA. Oh, so far we got one carryover A to B, A to C, A to C, A to B is not listed there. So you got 6 and got 3 left. So what we can do is at the end is try to estimate the number of carryovers by counting just the carryover pairs that we have in this particular sample. Our issue is that we have 9 cows, and I'm not sure that it can actually be balanced fully. So what we want to do is have each of these treatments. We're going to start with A, B, and C. That's essential. Now for A, we have two choices, A, B, C or A, C, B. We can try A, B, C because we have to choose one. And then B, we got B, C already. So let's try B, A, C. And then we got C. We have two choices here, but either of these is not, we're going to miss one out. So let's just try C, B, A. So if we count across the carryovers here, we got one of these, one BC, then BA, we have one, AC, we have one. Where are we now? AC. Then we have CA and A. Oh no, we have AB already. So this is row 3. My pen is a bit fiddly sometimes. So then we're looking at row 4, CB. Okay, let's call this C. B here. So then we got EA already. ACB, where CB is here. So that's row 5, row 6, BC and A. CA already there. So you can see there for the first 6, we actually have a reasonable balance because we got 2 each. However, for the last 3, because the numbers don't quite fit, we'll find that it's not balanced. We got ABC. So A, B, C, B, A, C. And then we got CBA, CB, and BA. Aha. So you can see there we have 4 of these carryovers and 2 of these carryovers. So this is not quite perfectly balanced as you wish to. If you switch this one around, maybe we can fix it. So I'm getting rid of this B. I'm going to change this to B. It's a very bad B. So we had CAB instead. So we're missing, this one is gone. CA is what we're given. This one is gone. We're adding on to AB at the top. So that's still imbalanced. So by counting the carryovers, at least we can say that I don't think there's any way, to my mind, that we can balance this property. But it's an interesting question to look at. So then, how would you maximize your power? So we want to consider that at the end of time period 1, we're going to have a washout period here, a washout period here. So in effect, we're going to have time is equal to 5 different things. We've got different treatments. We've got 3. That's that variable. We have a baseline for each of the 3 treatments, and then we've got our sample size of n cattle. So that means we can better tackle the next question. So think about variables that might affect. So if we have any particular cow, you have y, our observed value, and that's going to be a function of the baseline level for some treatment S. Then we have the effect of that treatment plus the effect of some carryover for the previous treatment, S minus 1, plus the time effect. So some time period K. So then we can think for the first ones. For the first ones, there's no carryover, but then for the subsequent ones, there is. So what we could even do here is also have a time period 4 here where we add on the same treatment again, C, C, B, A, B, A, C, C, and B to see if we can test the carryover onto each particular type. So then we just have simply to know for our model that K is equal to 1 to 5 time points. We're looking at animal Y, I. So I is some value going from 1 to 9. Treatments, we got 3. And then the carryover effects, we got 3 as well. So that means even though we only have 9 different cattle, so we can think that we got 9 by 9 by 5 different components of variation present in this. And this is Y is estimating their variability levels. So that means we can better quantify, what I should have put here is then there's some error associated with this particular animal. So EIS, or some treatment S, and some time period K. So normally if we're trying to estimate errors, we're assuming that EIS is some function of a normal distribution that we can scale with our data. However, this may have errors that are not of variables that are impacting our work, but are not recorded in this equation here. Okay, so let's move on to the next question. That's looking at the vaccine efficacy. Remember the formula here is you have 1 by A, if we have A out of B in the vaccinated cohort, and then we have the placebo cohort where it's C out of D are the numbers affected. That's how we get the percentage. So if looking at 70%, we can kind of think about how that would mean. So that would mean 1 minus 0.3 here. So if we've think about that, then if we've 1.3 here, we just have to put a 3 out of 100 divided by 10 out of 100. I think that would give us 0.3, which is 70%. Just using my numbers for studies are never going to be perfectly balanced. And that means then if we have the inferred group, we're looking at the same formula, except we're dealing with a more complex situation where we have 1 minus that group again, 3 out of 100. So that might mean that this is some value X out of 97 plus the second time period. So you got Y. Sorry, the other group, we might have 90 left over. And then we have our control group where we have some unknown value out of for an inferred vaccine group. And what we need to do then is kind of solve this using because you need this to be equal to 0.25. I think for this to be 0.85, you can imagine then that what we want then is kind of 15 out of 200 to be divided by, as a denominator, yeah, 100. Yeah, is that correct? Out of 200. So that's roughly what we'd want to achieve. Then question 10, when we're looking at predict, what we're looking at here is predictions refer to individuals. That's my band routing individuals. And that means we have to describe our data. We have to explore it in another cohort. And that can permit us to infer about population parameters. So maybe the mean expression of a particular protein of interest. But then if we're applying that to individuals, we have to have a high level of accuracy that this is another step on to make individual predictions. That's quite different from inference about the population mean. So if we're going to we can make predictions about individuals, but if we're going to make them with high certainty and low uncertainty, that means you have to have a very good model and very reliable data. So you have to build up a study through these stages to get to that stage. And you can read more about it in the Lee and Peng paper. And then finally, question 11, is transforming your range beyond log and exponential only permitted in research? Yes, you can transform your data further. It's whether that's sensible. The issue with transformation is that it may not make sense after transformation. And we look at examples where you can transform your data wildly into very, very different data, such that interpreting the results is very, very different. So this may make sense, and there are no rules, but there are clear consequences when it can go very, very wrong. So we'll look at that during Lab 1 itself.